In this video, I'm going to show you about time of concentration. Now, I'm going to use the TR55 worksheet 3, and that's over here. When the original TR55 came about, the time of concentration, or the length of flow for overland sheet flow, was 300 feet. Now, with the new worksheets that came up, it says that the length can only be 100 feet. And in the Windows version of the TR55, which we'll be using later on in this course, it only allows it to be 50 feet. So in this example, I've got a drainage basin over here, and the divide's already set, and the time of concentration flow path has already been delineated. But I'm going to show you how it breaks down and how to go about looking at time of concentration. The first thing that I want to remind you of is the drainage basin. The divide is when you're splitting the finding which area that actually flows to a point of analysis. So the basin divide is always perpendicular to the contour lines, and these are my contour lines. In addition, the time of concentration line is also perpendicular to your contour lines. Now, over here on this window, on this PowerPoint, I have is the design aids that you need for the worksheet. So I kind of pulled those out already, so it'll be easier to get the information. This information can be found in the TR55 manual, which is actually hyperlinked online already for you. So just look for that when you start to work on your homework. So I want to go ahead and go to the AutoCAD, and I'll start to draw where the time of concentration line or the flow path is going. In this example, we're going to have sheet flow, shallow concentrated flow, and channel flow. And the channel is either going to be arbitrarily given to you, because on this graph right here, or this topographic map, it can't be delineated without a little bit somebody telling us what that cross section of that channel looks like. Now, I'm going to go ahead and switch over to AutoCAD. Now you can see, if I zoom in, you can see how tight these contours are. You can see the little blue line. That's my flow line. So that's where the channel is at. So what I've done is I've arbitrarily created a channel that has a 6-foot wide bottom section, 12-foot wide top section with a depth of 3 feet. So it's going to be a trapezoidal channel, so we'll have to do some calculations on the area and the wetted perimeter when we get to our channel flow. So I'll also be using Excel in this program. But let's go ahead and get started on the first part of the spreadsheet. This project is actually going to be located in New Jersey, so we're going to call it NJ Site. Okay. Now, it's going to be designed by me. And I only usually just use my initials. When you're working in a company, that's fine. And then you put today's date. The location is in New Jersey. And I don't have anything more specific than that. So when we go to look at the 2-year 24-hour precipitation, I'm just going to use New Jersey, just to make this simple exercise. Now, it's going to be checked by your boss, whoever that is, when you get into your job. Check 1. This is going to be present condition, meaning it is existing as is today, not a developed condition of what's being done in the future. We will be looking at the time of concentration and not just travel time. Now, through sub area, if this project could be broken down into additional areas, then we might do time of concentrations on each sub area that we're looking at. But this one, we're just going to do it as is. All right. Now, the first one is sheet flow segments. So in this, let's go ahead and look at what our sheet flow is. When you look at sheet flow, you're usually looking at the contours that are at the highest point, and it's when water starts to flow before it starts to gather up depth. Not enough depth that it's in a channel, but enough depth that it's actually flowing as a shallow concentrated flow over the land. So the overland sheet flow is going to be up here in these two contours, because they're going to be your flattest area. So you can see the path that's already been delineated. It's going to flow from this point down to this point. So what I did in the AutoCAD drawing is I went ahead and drew up this flow path. So I'm going to bring that to the front. So it's going from the highest point. And the highest point elevation, if I come over here, is 314.7. and it goes down 2 contours. Now, it goes down 2 contours, and I just wanted to see what 300 feet was, so I drew a line straight 300, and I like to stop mine at known contours, so I'm not guessing between contours. So the distance from this absolute high point to the first set of contours, that's this flat slope here, is going to be 292 feet. So we already said that this table or this worksheet, if I typed in 292, watch what happens. It gives me an error. So what you have to do is you have to split it up. So it's going to have, since it's got 292, it's going to have at least 3 segments. So segment 1 is going to be 100 feet. I'm going to go ahead and put that in. Segment 2 is going to be 100 feet. Okay, now you'll actually have to pull up a second worksheet, and I'm not going to fill all this in, and I'm going to call this segment 3, and I'm going to call it 92 feet. Okay, now by doing this, you have to make sure all of the worksheets are grouped together. Now, if I was doing it in Excel, I wouldn't have to worry about doing it this way. I'll show you Excel in another video to do an actual spreadsheet for this calculation instead of using somebody else's sheets that have been developed. But I want to go ahead and show you the basics of how the TR55 time of concentration worksheets do work. Now, so I'm going to go ahead and back to the first one. Now, the description, it says surface description table 1-3. So I'm going to go back to here for the Overland sheet flow. Here's my roughness coefficients, Manning's in for sheet flow. So that's what it's asking. These number 1 and number 2 are asking what's the Manning's roughness coefficient from this table. We're going to say it's grass in this one because I don't know. Usually I look at aerials or I go out to the site. So in this one, I'm going to just call it dense grass. And it's going to be 0.024. So you can just say dense grass, and you can say 0.24. Now, in the next part, and I would do it again for on this one here, I would say dense grass, 0.24. All right. So the next thing it asks me is the 2-year 24-hour storm event. Now, I've already got ahead and Googled it and said, okay, NOAA Atlas 14, because that's where I'm going to get my precipitation. And it's going to be, usually it's going to be the first thing that pops up, the PF map, contiguous U.S. Precipitation frequency. So I've got the map up here. I'm going to go ahead and just write New Jersey. And we'll do New Jersey, New USA. It actually pops up if you look at the address, New Jersey to New Jersey. That's close enough for me today. So I'm looking for the 2-year 24-hour. Here's the 2-year, come down to the 24-hour. So that says 2-year 24-hour is 3.3. So I'm going to type in 3.3 here, 3.3 here, and lastly 3.3 here. All right. This is why I like Excel better, is because all my spreadsheet information will be all the same. Now, here's the thing. If I go back to my AutoCAD, if this was 314.1, 314.7, then the next contour down is going to be 312, and the next contour down is going to be 310. So what is the slope from 314.7 down to 310 at 292 feet? So what I did is I went ahead and created a spreadsheet, and I said, okay, for the Overland, I already did it for the shallow and channel. We won't pay attention to those right now. For the Overland, I said, all right, it's 292 feet. The upstream, that's the upstream point, and the downstream point's down here. So I put those two elevations in. Now, I wrote this equation. Basically what it does is it says inside these parentheses, I'm going to take the upper elevation minus the lower elevation divided by the total length. That's going to give me the slope of 0.016. So I'm going to type in 0.016, 0.016. All right. And now I'm going to type in, I'll get this last one done, I won't have to do it again, 0.016. Okay, so it's going to be 0.24 plus 0.51. You would need to write that down because it needs to be added to this. All right. Now, the next segment is going to be the shallow concentrated flow. Now, the shallow concentrated flow can be as long as you need it to be, but you do have to be aware when you're looking at your contours, if the contours change, causing it to change slope, you need to have multiple segments. In this one, I can look here and I can see that the contours are constant all the way down to this point here where I'm assuming it starts into channel flow or there's a stream. So I'm going to say from this contour up here at the end of my Overland sheet flow length, it's going to become it's going to become the shallow concentrated flow. So I went ahead and drew the shallow concentrated flow. Bring that to the front in this other blue color. And its length, again, I'm going perpendicular to the contour lines, is 366 feet. Now, I have to look at it and go, all right, what is the elevation that it stops here at? So I'm going to go over here because it's easier to see these. This is kind of blurry. Unfortunately, when pictures come in, they turn a little blurry. At this point right here is where I believe it changes. And if you follow this path down here, that number is 290. So I'm going from 310 to 290 in 366.77 feet. So I'm going to go back to my Excel sheet. And I say, okay, here is the shallow concentrated flow. Its length is 366. The upper up here is the same as the lower end of the Overland. And the downstream is the 299. So again, I'm using my formula of I subtract the elevations from each other, higher to lower, and then divide by the length. So that length is now, that slope is now going to be 0.055%. Well, you can tell by the contours that it is a steeper slope than the sheet flow slope. So that makes sense. So we're only going to use one segment. So I'm going to come over here and I'm going to go, okay, segment 1. And I'm going to, or you can call it, we'll call it segment 4 because we've got 1, 2, 3 for the sheet flow. Segment 4, and it's going to be unpaved. So now that we've got unpaved, we're going to have to go back to this here to figure out what the velocity is. We know that the length is 366, and we know that the slope is 0.055. All right, now the average velocity. So I'm going to come over here, not over there, sorry. I'm going to come over here and I'm going to zoom in. So I've got 0.04, now here's 0.5, here's 0.55. I follow this line over to this point right here. And then I follow it down. So I can see that it is going to be, if I count, I know that this line right here is 3. And if I count over, and I'm holding this 0.55, so that's going to be 3.2, 3.4, 3.6. It's going to be 3.7. All right. So we're going to say that velocity is 3.7. Now you can see that the total time that it travels over that steeper slope isn't that big of an effect on the time of concentration. Your largest time of concentration is almost always going to be in your Overland sheet flow, unless it's really short. The longer the Overland sheet flow, the more time it takes. Usually because your Overland sheet flow is usually flatter lands. Okay, not always, but usually, and especially here in Florida. So now I have to look at the channel for it. So I'm going to go ahead and go back to my AutoCAD, and we're going to say that, let me pan down so you can see this. We're going to say that it's going to go from this point here all the way to the point of analysis. So if I'm looking at this, the point of analysis, just so we can see the easier to read the contours, there's 280, there's 278, 276, 277, so I'm sorry, 278, 76, 74. We're going to say that's 273. Okay, we can see 272 here, so we'll call that 273. So go back to my Excel just so I can get the slope. So we said, all right, started at 290 as an elevation upstream, going to 273. Now I went ahead and drew the flow path line here. So I'll bring that to the front so you can see it. So here is the flow path line, again, perpendicular to the contours, and the length of that line is 801. I'm sorry. So the slope, again, the equation is change in the elevations, so I subtract the two elevations, higher or lower, and then divide it by the length. So now I know my slope. But here's the thing, is I don't know the cross-sectional area, I don't know the wetted perimeter, I don't know the hydraulic radius. If this was truly drawn to scale in AutoCAD, I could figure out those pretty easy, and I'll show you what I mean. So here is the cross-sectional area of the channel. So it's got, if I click on the line, it's a 6-foot bottom length. It is a 12-foot top. I'll draw a line from the end point perpendicular here, and you can see it has a length of 3. Now I'm going to type in BO for boundary, and I'm just going to pick it, hit enter, and now I'm just going to move it up so you can see what I'm doing. That area is 26.4853. That is going to be in square feet. I'm going to type in P-edit, M for multiple, and I'm going to highlight all those and hit enter. Again, you don't have to do this in CAD. I'm just showing you because I use CAD for so much. And I'll say yes, enter. Oops, P-edit, M for multiple. I need to work and not talk. J for join. Enter because I want a fuzz distance of 0, and enter again. So the length, which it would be my wetted perimeter, is going to be 14.41. Now, here's the other thing, is I'm going to show you how to do it based on using these formulas here. Okay, so usually, almost always I do everything in CAD because it's a lot easier. But I'm going to show you how a little bit of Excel can be used. All right, I'm going to go ahead and pull this over. Kind of get situated so you can see everything, and I can show you the formulas. The first thing that I did in Excel is I went ahead and set up these cells so I could write 6, 3, and 12 in. And I'm going to arbitrarily give you a Manning's N of 0.032. Now Manning's N, excuse me, Chow wrote a book, and he did a lot of research, and these values can be found in numerous books. So I'm really comfortable with using these values because I've got textbooks from when I went to school that was written by Chow and a lot of research data. So these are Manning's N for channels. Notice mine's 0.032, so you can see the normal. It's a clean straight channel, no ruffles, no pools. If you've ever played in a stream, you know what a riff or a pool is. It's just, that's a whole different topic. I'm just not going to go over that. All right, so here's the thing. So we know what our Manning's N is because we're going to be using this formula here, 1.49, the hydraulic radius, 2/3 power, slope of the channel to the 1/2 power divided by the Manning's N. But we have to find out the hydraulic radius. The hydraulic radius is the area over the wetted perimeter, where we know the area of a trapezoid is going to be the top width plus the bottom width divided by 2 times its depth. That's basically what this formula is here. But sometimes the slope is actually different on each side. when we design a channel, we almost always, let me show you, we almost always make these side slopes, the horizontal to vertical side slopes, the same on each side. But that's not always true. Sometimes it's steeper on one side and shallower on the other side, depending on maybe if it's a roadway design. So sometimes it could be, okay, it might be steeper on one side or shallower on the other. It really depends on what your design constraints are. But these are actually one-to-one slopes, because if you go over and up, it's going to actually go over 3, up 3. So your horizontal to vertical is going to be 3 to 3 or 1-to-1. So the Z, the side slopes in here, the Z is 1. So the area of the trapezoid, and let me make that a little bit bigger, is going to be 27. If using my formula of taking half of the top width plus the bottom width and multiplying it by the depth, okay? So in this sketch, the area, as you can see, is 27. Now, the wetted perimeter is going to be the bottom width, that's what BW stands for, bottom width plus 2 times the depth times the square root, that's what SQRT stands for, the square root of the Z factor for the slope squared plus 1. So if you look at the formula here, you can see I'm taking the row to column, and that's what the C8 is. If you haven't had Excel, send me a message and I'll send you some general information on Excel. So we've got rows and columns. Our columns are C's, our rows are numbers, or our columns are alphabet and our rows are numbers. So we've got C8, so that's cell C8 plus 2 times C9, which is the depth, times the SQRT, that's the square root of the Z factor, which I just wrote over here as 1, raised to the 2 power, or squared, plus 1. And you have to have parentheses to close everything off, okay? So the wetted perimeter is 14.49. I can expand out those values, and you can see it's 14.4853. This is why I love using AutoCAD. I can get all my data from AutoCAD and the Properties palette. The Properties palette, if you ever lose your Properties palette, you can type in PR and the Properties palette will come back. All right, so now I have to figure out my hydraulic radius. And we said the hydraulic radius was area over the wetted perimeter. So all I have to do is take the area cell, the F10, so there's F10, divided by G12. Here's my wetted perimeter. So I get a hydraulic radius of 1.86, okay? And then the velocity, I can put it in an Excel spreadsheet. Here's the formula, what it looks like, 1.49 divided by N times, and I can put these in parentheses. I like parentheses. I like to make sure that everything is broken down in the orders of operation. So 1.49, I've got a typo there. It should be 1.49 divided by the Manning's N multiplied by the R to the 2/3. So G14, you can see G14 raised. That little caret means to the power of, and I just put in parentheses 2 divided by 3. That's 2/3 power. Times E5, that's my slope. That's the slope that I figured up here. So I don't have to keep rewriting all these numbers. And it's to the power of 0.5. Okay, so I hit enter. Now I can come over here. So our segment is going to now be 5. The cross-sectional area we're going to say is 27. The wetted perimeter. And here's the other thing. Notice everything in blue you type in and then it calculates for you. So the wetted perimeter was 14.485. And it automatically fills out the hydraulic radius. Yay, it's the same value. Okay. And then the slope was 0.021. And the Manning's roughness coefficient is 0.032. And the flow length was 801. So it figured out my velocity. Look, my velocity. So I've got a little bit of rounding. The rounding is probably in this worksheet and not Excel. Well, I'm pretty sure it's not Excel. So Excel uses all of its decimal places until you decide to round. Okay. Now, take a look. So the time is only 0.02. So here's the thing is these values for the shallow concentrated flow and the channel flow doesn't give you a lot of time of concentration. All your time of concentration actually came from that sheet flow at the very beginning. And remember, we're still missing 0.24. So if it's 0.56, so if I move this over just to show you, if I said TT, travel time of sheet flow, is equal to, and I would say, I like to have everything aligned really nice, is going to be 0.26. So you put an equal sign. An equal sign is always required for the Excel sheet to do a formula. So my formula is 0.026 plus 0.026 plus 0.024. And then TT of shallow flow. I'm not going to write shallow concentrated. Again, I like to keep mine. I go to alignment and send it. And that was 0.03. No, I don't need an equal sign here because it's just a number. And then TT of channel flow is equal to 0.02. So if I go equals and I type in the word sum, it allows me in a parenthesis, open parenthesis, it allows me, and I select all those and then close that parenthesis, it allows me have a time of concentration equal to, again, getting everything organized. This is what I said about when you have to submit. And this is in hours, okay? Oops. I want to send it there, okay? So the time of concentration for this project here to get from this point way over here down to the point of analysis is 0.576 hours. All right, so that's how you use the TR55 worksheet for time of concentration or travel time, and just a little bit of AutoCAD examples and a little bit of Excel. So when you're in this class, it's not just, you're not just learning how to use hydrology and hydraulics to design, but I'll show you how to use a little bit of AutoCAD in your projects, and then how to use Excel in your daily life also, because Excel is extremely important. So that's it for this video. If you have any questions, just send me a message. All right, thanks.